All right, good afternoon. So welcome back to Calc 2. We are in the midst of doing a review, or at least the beginning part of the review for the first test, which is going to cover Chapter 6 and Chapter 7. Well, up to numeric integration. I'm not going to ask you numeric integration on exam. Okay, so up to that. It'll still be due, but I'm not going to ask you a question. We might do a project with it a little bit later. Okay, so let's go ahead and share my screen here. All right, and let's get busy with some work here. All right, so the first one, I'm going to go ahead and hide that. So the first one that I'd like to talk about is something that your book doesn't cover explicitly. They just throw it in and occasionally and assume that you are just going to handle this like a pro. Okay, but they don't explicitly go over it anywhere. That's what happens if we have something like right, what happens if we have something like the integral, right? We want dx over, and we'll put in an x squared minus 2x plus 5 here. All right, so here's the problem. You can't factor that. So we could say that, well, this is equal to some kind of a bx plus c, x squared minus 2x plus 1 equals, right, equals dx over x squared minus 2x plus 5. And about all you can do with this is say that whatever we have here is equal to 1. That's really not going to help, okay? So 1 dx here. So we can multiply through. It's really not going to do us a whole lot of good here, all right? All we're going to do is get c is equal to 1 and b is equal to 0. It's just not going to work. Okay, so you're stuck back to here again. Like, yay, we're back to this. Because there was no partial fractions, plural fractions, to do decomposition on. Okay, so if you're going to do partial fractions, you need more than one. Otherwise, you get the same thing back. All right, well, that's, we're done. Wonderful. If I just set u equal to this bottom thing, right? And we take our derivative, du is equal to 2x minus 2. I'm like, great. Oh, I don't have an x up here. I have a dx. I don't have an x. Okay, so there's nothing I can kind of deal with here. Okay, so we're at a loss. All right, let's see. What other things could we do? We've got an x squared. But maybe we could think about some kind of way of making this a tangent. We will, but as it is, like I don't have like this format of saying u squared plus a squared. I don't have this. So what are we supposed to do? Well, you may perhaps remember if you had algebra with me, or with, actually I think everybody teaches this in algebra, or pre-calc, because they definitely teach it in pre-calc now, completing the square. You say, what am I ever going to need that for? Well, if you had ever had that thought of when am I going to need this, today is your lucky day, because that's where we're going to need it. So what we're going to do here is we're going to complete the square on this. Right? We're going to say this is x squared minus 2x plus 5. All right. Now, if you remember how to do complete the square, right, you identify the middle term, right? That's the middle term. If I put this in quadratic formula, right, a would be 1, b would be negative 2, c would be 5. So we're going to identify the middle term, b is equal to negative 2. Now we're going to take half of it. It's equal to negative 1. And then we're going to square it, 1. And this is going to be the magic number that lets you complete the square. But I just can't go around adding 1 to things. If I'm going to add 1 to things, I'm going to have to subtract 1 from things, right? Because we can only really add 0. And then we're going to group these together. We're going to group these together. So this is now going to be x minus 1 squared plus 4. Now, conveniently in this question, that happens to be a perfect square. This isn't necessarily going to happen, and nor does it really need to. Okay, because we could divide things up into square roots and things. We're okay. But as it is, you know, it came out of a textbook. It's perfect square. Okay. So what do we do with that? Okay, great. We have an integral of dx, x minus 1 squared plus 4. And so that's not really helping. I'm like, well, it kind of does, because this shape reminds me of that shape. And that's an inverse tangent, and that's something we can't integrate. So maybe we can hammer this into the right format to see if we can make this into something that looks like an inverse tangent. Okay, so why don't we say let u is equal to x minus 1. Du is very conveniently dx. All right, so here we have integral du, and I've got a u squared plus 4. Hey, that's looking pretty good. Now what I'm going to do next is I'm going to go ahead and pull this 4 out. So I've got a 1/4, I've got a du. Technically, I've got a u squared over 4 here plus 1. We did one like this yesterday where we said this is 1/4, and then we have a du. And then I said, well, this is really u over 2 squared plus 1, right? And now what we're going to do is, because I don't like it when it's fractions and it's messy and it's horrible, is let w is equal to, excuse me, right? And dw, right, is equal to half du. So du, right, as a scaling factor is equal to 2 dw's, and w is equal to u over 2. So here's my substitution. We have a 1/4, right? We have a 2 dw up here because du is directly equal to that. Okay, so I'm just substituting. I'm not trying to match or multiply it. I'm just substituting it. And then here we have our w squared plus 1. Pull this out. And if I didn't know better, I'd say that looked like an inverse tangent. So let's go ahead and integrate that. And now we get 1/2. We get inverse tangent of w, all right, plus c. Okay, so that's going to be 1/2 inverse tangent. You say, what the heck was w? W was u over 2, all right? So what the heck was u? U was x minus 1. So it's going to be inverse tangent x minus 1 over 2 plus c. And that is that integral. All right? So, like I said, I don't know if your book covers this exactly, precisely, but I think it does give you some problems where you have to use this technique and they just assume, well, of course you remember how to complete the square. Why wouldn't you remember that with perfect recall? Right? So, yeah, that's a thought. Okay, let's see here. What else to go? Oh, we can do this one. Okay. So, integrate. And then here we have 5 minus 4x minus 2x squared. So here's what my thoughts are on this one. Okay, we're going to have to complete the square because, again, no u substitution is going to help that. All right. Integration by parts inside of a square root, it's never going to get smaller. It's going to be horrible forever. Okay. So not the best technique. All right. We're going to have to do a complete the square problem. Okay. And quite frankly, I am terrible at doing complete the square when the coefficient isn't a 1. So and I know I learned this a little bit different than you guys do today. But what I'm going to do is I'm going to go ahead and write this. Okay, there was a lot of borrowing and making everything kind of work out when I did this, the way I was taught it. It was not a very memorable method. There was a lot of little things and exceptions and horrible things. And this does have some exceptions and some weirdness going on. But what we're going to do is we're going to factor out a 2 here because this 5, this will come. Okay, we'll take care of this later. But right now, let's just deal with what's going on here. All right, so I've got a -2 x squared, right, plus 2x plus 5. All right, we'll just push this off to the side. We'll get back to it. Pull the -2 out in front, because the thing about complete the square is that, the method I just showed you, it only works when this coefficient here is a 1. So every time this isn't a 1, we have to force the issue and make it a 1. Right? So again, let's identify the middle term. Middle term over 2, and middle term squared. So we're going to add 1. We're also going to subtract 1, because we can't just go around and doing that. Now, when I added 1, it was inside of this bracket, so it isn't really 1, if you know what I'm saying. But we got to subtract the same thing, which again isn't really 1. So let's deal with that. It's -2. What do we have here? X plus 1 squared minus 1 plus 5. Okay. Now, we pulled this out. We're going to put it back in now. Okay, because now it's time. So this -2 is going to apply to both of those. Okay, and you see how doing it this way kind of tracks those negative signs and tracks the scaling factor, and you don't have to do anything like trying to remember like what to borrow from the no, we're not doing that. Okay, I mean, you can if you'd like. I'm not going to, if your tutor showed you a way, if you have a tutor that showed you a way to do complete the square, and you're like, that makes perfect sense. My teacher's an idiot. He doesn't know what he's doing with this. Like, I'm not that proud. You find somebody, some high school that shows you how to do this, or you have a tutor that shows you how to do this, older sibling, parent, don't care. Okay, it's fine. All right. So yeah, what we're going to do next here, right? So now we have, all right, I'm going to go ahead and turn it around. So what we're looking for is we have a dx. We have a 7 minus 2 x plus 1 squared. And this is all inside of a square root. Now I'm thinking to myself, this has got to be an inverse trig here, right? Because there's a square root. So it's got to be an inverse trig. But I don't like the way this looks just yet. So why don't we do a little bit more here to make this worthwhile, to make this something that we can recognize. So we're going to let u equal x plus 1 du, again, very conveniently, dx. All right. So we're going to have our scaling, we're going to have our integral. We have a dx. We have integral, or square root rather, 7 minus 2 u squared. Okay. So again, almost a triangle, not quite. So the next thing we're going to do here is I'm going to factor out a square root of 2 here. I'm trying to match it to the form I have that I know how to do inverse trigs. Now, if I take a square root of 2 out of here, that takes care of this, right? Because it's inside of the square root. So it's just effectively a 2 if I'm looking at it inside the square root minus u squared. Okay. Now, 7/2 inside of a square root that we're going to deal with a triangle, this is going to be ugly. All right. But it is just a number. I mean, if you wanted to say 7/2 is equal to a, right? And then put that in here, or make it even better, a squared, right? That's fine. Okay, so if it helps you, because maybe, it's been a while, a couple of days since you did this homework, and you'd rather see it as an a squared minus a u squared, so you can remember, like, oh, that's right, this one's supposed to be signed, then you go right ahead, okay? One thing that I watched, so I took a couple of engineering classes over at UNM, and the thing I would watch is, they're all very good. Okay, I'm not going to tell people that those were bad students, because they certainly were not. They were all good students. They were all, they were just like you guys. Okay. But I did notice, so if you're an engineering student, I did notice as soon as they took the 7/2 out and they said, well, this is going to be our thickness, so we're just going to call it T, and it's a parameter, or we're just going to call it A because it's a convenient number. Because I'll tell you, in real life, this is not going to be 3/2. Okay, or 3.5. This is going to be some 4 decimal long thing that somebody came up with. So it will help you to treat constants as something you can just give a handle to, and then move this around. So you don't have to deal with a 4 decimal or 6 decimal number going on here. Okay. So it really will to help your ability to abstract. And when you come across this, because I watched that test, and when they did the problems, and it was a problem that like any C student would have been able to deal with. Okay. But as soon as they took the step in halves and they said, well, we're going to call that a T. Okay, the thickness of the bottom here is going to be T, rather than the 1/2 inch they usually put in, completely fell apart. Completely. So it's really, you don't have to replace all your letters, all your numbers with letters, but every once in a while, wonder, like, maybe I give it something else here and see what's going to happen. Okay, enough of that. So we have we have a squared is equal to 7/2. Okay, I get an a squared minus a u squared. That's a triangle, isn't it? Right? So we have a dx. We have 1 over root 2 as a scaling factor, right? And the root 2 came because this was inside of a square root. That's how we had to pull it out of a square root. Still got to keep that here. And then we have a squared minus u squared. Okay, so different a, right? Pythagorean theorem. So if we do this, we say b squared is equal to c squared minus a squared, right? And then b is equal to the square root, right? That's the triangle that we have, okay? So if we make a little triangle here, right? What's the c squared, right? The c squared looks like little a. Tell you what, let's change, let's say, come on, c squared. That makes it real easy to remember. Okay, so if we have our triangle, right, here's our c, which is equal to 7/2, right? Here is our, usually like a to be the adjacent one. Let's see, c squared minus a squared. Yeah, let's go. I might change where this is in a minute. So this is just going to be u. No. We could do that. We'll make this one u. And this will be c squared minus u squared square root. Okay. So that's check, right? That's our triangle, right? So the hypotenuse squared minus the side squared is equal to the other side, right? The square root of the other side. So if I squared this, I would get c squared, right? Good. Okay, so what we're going to do is we're going to say that sine of theta, right, is equal to u over whatever c was. So u is equal to c times sine theta, okay? That's why we have ABC as constants. Okay, everything else can be a variable, but ABC are typically constants. And du, right, that's going to be c times cosine theta, d theta. Okay. Why did I not want to make this one why did I want to make this one the u and then I changed my mind? Is because when I take the derivative of cosine, we get a negative. So it really is up to you. It's just what poison do you want? Okay, where do you want that negative sign, or do you want that negative sign? And if you could move it, you probably should. Okay. So we have u is equal to this thing, right? So when I go back in, right, we've got right here's my integral. Well, what's my du? Is c times cosine theta d theta, right? What's this going to be? This is going to be square root c squared, right? Minus c squared sine squared theta. All right, because u, right, u is equal to c sine theta. So if I square it, c squared sine theta, sine squared is. I'm going to pull out the c. How's that look? You glad you carried that around as a number? So here we go. Okay, cosine theta on the top here, d theta. All right, now what do we have here? All right, remember that sine squared plus cosine squared is equal to 1. So cosine squared is equal to 1 minus sine squared. So we have the square root, right, of cosine squared down here. That's going to cancel out. So we have 1 over square root of 2. If cosine over cosine, oh, that's 1. D theta. Man, that's a physics integral if I ever saw one. That's nice. Okay, and I do tease the physicists because it's not because I'm teasing, it's not because I'm trying to belittle. I am legitimately impressed by all of the work that physicists do to come down with an integral that looks like this. Okay, that is just amazing with how they do that. So it's respect and I'm impressed, not trying to belittle. Okay, theta plus c. All right, there we go. What the heck is theta? Right. Well, if sine theta, right, is equal to this, then shouldn't theta equal the inverse sine of u over c? Sounds good. So we have 1 over the square root of 2, inverse sine, okay, and then we have u over c. So it did come back and get us, okay, and what the heck is u? What the heck is c? Right now we got to go back and we got to fix everything and make it look like we actually worked the problem that was given to us in the book. Okay, so what's u? U looked like it was x plus 1. And then c, what the heck is c? C, well, we said c squared, right? C squared was equal to 7 halves. So since c squared was equal to 7 halves, c is going to be the square root of 7 halves. Okay, we could do this and get this a square root of 14 over 2. So this is going to be square root of 14 over 2. Okay. So that could be our answer here. Actually, you know what? Let's go back and make this just let's go back and make this 7 over root 2. That way when I divide right by my fraction, we get square root of 2 over square root of 7. Okay. So now we have yeah, I guess it still worked. So we have 1 over root 2. Oh, there's always a plus c here. Not the c. Sorry about that. You think I'm bad? I had a teacher that used I for the imaginary number a counter and a counter and a summation. And I think we were working on something with current in it. So it was a variable. He didn't use capitals. It was all little I. So it was a variable, it was a counter, and it was the imaginary number. You just had to know what it was from the context. So I apologize for the fact that I've used a couple of letters too many times. But I have a ways to go before I'm quite at that level. Okay. But if you would rather use something else here, I mean, this C, completely arbitrary. All of the C's that I used, right? I called them because it felt like it would match a pattern. Okay, I didn't really care. All right, let's see. Do we want to do one more of these? That one looks like we did something like that before. But yeah, why don't we do another one? Okay, one more like this. Okay, so here we go. How about we have an x over, we have an x squared plus 4x minus or plus 8. Let's change that to a minus. Where's my eraser? There it is. All right, dx. And let's see here. What are we going to do with this? Let's we're going to, again, right? We could look at that. Actually, there's a couple of things we can do. We could say let u equals x squared minus 4x plus 8. Du is equal to 2x. I've got a 2x minus 4. All right. And like, what do you do here? I'm going to tell you it's going to be completing the square. Okay. But you don't have to. Okay. What we could do is we could subtract 2 here and add 2. And we're going to have an x minus 2, and I could multiply this by 2 and put a 1/2 out in front. That looks like 2x minus 4, doesn't it? And we have a plus 2 sitting over here. And now we have this integral. And we have that integral. All right. Well, I'm looking at this. See, this one we figured out, like, what was going to be my u? Like, okay, we got a u, then we forced a du here. This is not going to be fun. Okay, we're going to have to complete the square. It's going to be another inverse tangent. It's going to be delightful. Whereas if we do this, great, we got a u and a du. We're set. We could just integrate this to get a natural log, but we still have a lot of work to do here. So I'm wondering, maybe, yeah, well, why don't we complete the square first and see if that works out a little bit better. So we'll put this on hold. And we might come back to it. All right. So let's see what else we can do with this thing. What if I just made I did the complete the square thing first? Because I'm going to have to do it anyway, right? We're going to have to do it anyway. So why don't we just say this is, why don't we say we have x squared minus 4x plus 8. Our middle term is negative 4. Middle term divided by 2 is negative 2. And b over 2 squared is equal to 4. Okay. So what we're going to do here, this one, there's a couple of ways to think about this. All right. So the way I was taught, you would have borrowed 4 out of here and put it over here so that you would be able to complete the square. And so this would be a 4, and then we'd have a 4 here. So on this example, it doesn't look too bad. All right, so that's my integral on the bottom here. So why don't we let u equal x minus 2. And while we're at it, why don't we say u plus 2 is equal to x? Like, why are you pulling that out now? Like, what's my numerator? It's just x. Okay, that's why I pulled that out. So we're going to have, okay, we have in the u world, u plus 2. Okay, notice this 2 is really this 2. Okay, and this is divided by u squared plus 4 d. Excuse me. All right. So yeah, that's all the fun that we're going to have there. So we are effectively still back right, in this spot. It looks a little nicer here. But unfortunately, we didn't really see, there was, in the end, there was no clever way to do this. We're still stuck with exactly what we would have had here, except that it's a little bit cleaner and a little bit easier to deal with. Okay, this one, let W equal U squared plus 4 dW 2U dW. So we can go ahead and say this is 2W, I'm sorry. Let's do two things here. Let's do it this way. Let's say this is du is equal to dW over 2U. We're just going to directly substitute. Okay, so we've got our integral, we've got our U, we've got W, right? Because U squared plus 4 is W. And in our du, I don't know if you guys can see that. Our du is equal to dW over 2U. All right, you see what happened there? We just substituted it. Now some stuff cancels, doesn't it? That cancels. So now we've got 1/2 integral dW over W. Okay, plus. Now we've got this business, all right? This guy here, this is, right? We've got to pull a 4 out, so we've got we've got our 2. Let's get rid of that. All right, I've got my 4, and I've got a du over U squared over 4 plus 1. Okay, so you see what's going to happen here is we have a U over 2 squared plus 1. I think it's the same problem we did before, isn't it? Right? Where we set W equals U over 2. dW was equal to 1/2 du. du is equal to 2 dW. So when I go ahead to factor everything here, we've got a 1/2 out in front from this. We've got a 2 dW because we're just substituting. And then this is going to be a W squared plus 1. Right? Oh, if I would have thought to line that up. Okay, so here we go. It's a 1/2. That's natural log, right? Natural log W UZW. Let's go with V. All right. Okay. Plus, right, those cancel. We have inverse tangent, right, of V plus C. Now we get to go back and deal with all the substitutions we made. Okay. So this was W is equal to U squared plus 4. So we have tangent of 1/2 natural log U squared plus 4. Like, why did you drop the opposite values? Because U squared plus 4 is always positive. Okay. Inverse tangent. Inverse tangent, what the heck was V? Okay, V was U squared over 2. C. All right. We have 1/2 natural log. What's U squared? What's U? U was all the way back up here. Oh my goodness. Right, all the way back up here. It was x minus 2. Plus inverse tangent. What was that U? Was that a different U? God, I hope not. No, I don't think it was. I think we're still x minus 2's. All right, so here we go. Well, that's not a U squared. That's just a U. Or do you rather? Oh, no, it is U because we had to change that, didn't we? No, it's U over 2. It's not a squared. Let's go back and double check this. There we go. Okay. And we have tangent, and we have x minus 1 over 2 plus c. See that? Piece of cake. Only 3.5, 4 or 5 dozen pages, and we're set. Okay. One of my teachers say, it's after a page or two of algebra. Like, it's a page for you. For me, I got to work this stuff out. This is more than one page. Okay. So, yeah, that's what you do with that. Like I said, I don't think your book explicitly covers any of this, but they'll just throw it in at you as a question once in a while to say, hey, remember how to complete the square? And then you could use all the techniques that you remember from before. They're a little sneaky. Okay. So just to reiterate, for next week, we are going to be hitting, we're going to be hitting reviews for everything we've done up until now. If you guys have specifics that you want to ask about, please do that. I will be putting up our pre-test and then our test next week so that we can get get that done. Okay, if you haven't done quizzes yet, please do quiz. It's not a real quiz. I don't care if you get them right. I just want you to turn on respondents and see how it goes. And if it works, great. If it doesn't work, well, we'll figure something out. All right. Everybody have a good afternoon, and I will see you next week.